one of the problems, not just of this lecture, but of the Stardust project. So, I will have to start with the same cautionary word, more or less, used by Manios this morning. That is, please be patient if I say something that looks a bit trivial to you. I have to make sure that everybody not only knows the same thing, but even more or less with the same, even calls it in the same way, which sometimes is a serious problem, and maybe even all have to understand the common notation. So I will begin with something rather basic, and also in reality quite old. That is, 80% of the first lecture has only the goal of showing something which was known to Carl Friedrich Gauss and published in 809. Okay? But since Gauss is one of the most important mathematical geniuses of history, what he did was quite significant and still is today. So the first thing, which is a small contribution I think I will give, is I will try to describe the problem of orbit determination as a mathematical problem. That is, in terms which are consistent with the formalist method of 20th century mathematics. What is orbit determination is intuitively known to, I think, everybody. So let's try to give a formal definition. The formal definition is that you need three elements, three mathematical structures. The first one is a dynamical system. That is an equation of motion, which is an ordinary deterministic equation of motion of the form of an ordinary differential equation like this, or can be second order, but doesn't matter. And y is what we call the state vector. And note that already the right-hand side of the differential equation contains some parameters, which are called dynamical parameters, which may not be known. A typical example, the mass of the planets. Of course, the solution depends upon the initial condition, which are the state vector at some time, which in astronomical terminology is some time called epoch, t0. And all the orbits together form a general solution which can be expressed as a function of time, initial condition, and dynamical parameter. The second element of the orbit determination problem are the observation. Observation means that there is some function, which I am calling capital R, of the state, the time, and some other parameters, which may be called cinematical parameters. The most trivial example is the coordinates of the observing station. The result depends from where we are looking from. And then this function, the only thing we need to know is that this function is differentiable. Then we do the composition of the general solution with the observation function, and this we call the prediction function, means that given the solution, therefore initial condition and dynamical parameter, and also the kinematical parameter and time, we can compute what the observation should be at a given time, according to our observation model. Note that this also is deterministic. We are assuming that there is nothing which is probabilistic or random or anything like that, stochastic, in these two functions. Okay? Now, what happens is that, let's suppose we have observation at time ti, number of them, m. Then the result of the observation is typically not equal to the prediction. And the difference is the residual, which for an ancient tradition is observed minus computed. Okay? Now, one small detail we might not think important, the observation function is not always the same. You might be observing maybe the even or the odd observation are right ascension, the even are declination, or the odd observations are range and the odd are range rate. Doesn't matter. Anyway, you can assemble all the residuals into a vector, and this vector is a large number of parameters because you observe it many times. And this vector residual is a function of all the variables: initial condition, dynamical parameter, and even kinematic parameters. Now, I repeat, so far I introduced nothing probabilistic or stochastic. So where does the probability come from? The problem is that observation contains an error. The concept of measurement without error is against the most fundamental principle of physics. There is no measurement without an error. So even if we were more or less the god of Laplace, and we would know the exact value of initial conditions of the dynamical model, that is the dynamical parameters and the kinematic parameters, as our model was perfect, still the residual would not be zero. Even the values are right, or the best possible, there will still be a residual, and this residual would be a random variable. Therefore, the vector epsilon, which is the vector random variable, which contains the set of all possible observation errors, which are contained in each observation, has to be modeled in some way. Now, this can be done in two ways. With a true probabilistic model, which we have, as an example, a probability density function, which has an explicit formula for all observation and all the observation together, or maybe as a set of inequalities. We describe the observation rate we rate as acceptable, of the kind the errors cannot be larger than this quantity, or the standard deviation of the errors cannot be larger than these quantities. Now let's get to the point which was invented by Gauss more than 200 years ago. It's the idea that you define a target function, which is a function of the residuals. This function is not completely arbitrary, to be honest. It needs to satisfy condition of convexity and regularity. Practically speaking, must have a well-determined minimum, and possibly single minimum, as a function of xi. Otherwise, you get strange results. So we'll take the simplest example, in which Q is just essentially the sum of squares. Typically, the sum of squares of residuals is normalized by dividing by the number of observations in such a way that this is actually variance in the sense of statistics. And this quantity is Q of xi. Now, the next step is that, of course, Q of xi, if xi is a function of all the parameters, then also Q is a function of all the parameters. Okay? The next step is the most important of them all, and is often forgotten. Now we have decided which are the parameters to be fit, to be adjusted. Which are the parameters we don't know and we want to solve for. It's not necessarily the case that we want to do this for all parameters. Just an example, since we are going to speak about asteroids, make an asteroid example. The coordinates of the station cannot be determined by the observation of asteroids. Okay? If you observe Earth satellites, you can use this observation to compute the coordinate of the station, but not if you observe asteroids, because the asteroids are too far, so to speak. So, as an example, you will not put in the list of parameters to be determined. The initial condition, well, initial condition you have to solve for anyway. It's kind of minimum. Of mu, do you know well enough the mass of planets? Or you have to solve for the mass of planets as well? Are there other dynamical parameters to solve, like the one depending upon non-gravitational perturbation? This is a good question. So you can think to the simplest orbit determination problem as the one in which you are solving exactly for initial conditions. So roughly speaking, the number of variables you are solving for is 6. But it can always become more complicated. Now, so what is X? X is the set of parameters you want to solve for, is a subvector of this one. Only selected some of them. What happens to the others? Or the other parameters are left, the terminology in use is that these are considered parameters. All the others are left at assumed value. That is, you are implicitly assuming that they know them, and they know them well enough so that any error in these will not disturb, decrease the accuracy of your computations. Then the function Q is a function of X. At this point, the minimum principle says that let's use this terminology, the nominal solution is the point X star in the space of parameters we have selected to adjust, where the target function has its minimum, which we will call Q star. Now, I will not dwell very much into this in these lectures, but you should not neglect the point that there could be multiple minima, and Q star could actually be a local minimum. And this, in fact, does happen, although not much in the example I will do in these lectures. The principle of least squares is just the minimum principle with a target function, the sum of squares. In reality, this can be generalized to some other quadratic form, but anyway, the function Q is not more than quadratic. Now, an important point which has to be stressed is that nobody is suggesting that the asteroid must be exactly where the target function is a minimum. This is not implied at all. The real solution must be near there. But what does near there mean? If you adopt what I call the optimization interpretation, X star is the optimum point, but values of the target function which are immediately above the minimum are also acceptable. This implicitly defines what I might call a confidence region, which is a region in the X space such that the sum of squares is not Q star, but not too much above it. And there is, of course, one free parameter in this, which is this confidence parameter. So this solution corresponds to error larger than X star, but still compatible with the quality of the observation as we know it. As it is rather obvious, is that the choice of value sigma is not trivial. So this is a way of thinking, very simple mathematically, but practically to know which value sigma you should use is tricky. The alternative probabilistic interpretation describes the observation error as random variables with an assumed probability density, and therefore, as a result of this assumption on the errors, the result must be expressed in probabilistic terms as well. Now, few words on how the least square problem is solved. One conventional, of course, let's suppose again that we have a simple sum of squares of the residuals. The point is that the function of Q as a function not only of C but of X is differentiable. Therefore, we can compute its first and second derivative. However, what practically happens is that the matrix B, which is called in textbook design matrix, is a matrix which has a number of rows equal number of observations, number of columns equal the number of parameters which are included in the solution, and M must be larger than N, and then H is a complicated three-index array. The partial of the residuals are can be computed by a chain rule. Now, this chain rule is a little bit complicated because the observation depends directly only upon the parameters nu. So in the case of the asteroid, forget this term here, it does not occur. The derivative residual is the derivative of the observation with respect to the state. So you have an angle of position. You can compute it as a differentiable function of the position of the asteroid. You can compute directly the derivative, and then you multiply by the derivative of the state as a function of the initial conditions. The formula for H is quite complicated. If you want to find the minimum, you use the standard method. You look for the stationary points, and you write a set of n nonlinear equations in n unknowns, the Q over the X. When we have nonlinear equations, the first thing we would think is to use Newton's method. Newton's method uses the computation of the second derivative. Then you write a Taylor series like this, in which you are currently, your current conjecture on the state on the vector to be determined is xk. you expand in xk to find the value that the gradient you want to set to 0 would be at the point x, and if impose that it is 0. Of course, here I have higher order terms, which would contain the square of the different x minus xk. Therefore, I can compute by I jump one passage, these terms, coefficient 2 over m goes away, and what is left is this C nu, which is this matrix here, times the solution minus the xk equals this term, which is a function of the residual, plus higher order terms. So if I just neglect the dots, that is a linearized equation, I get that the next approximation to the solution, xk plus 1, is xk plus the inverse of the matrix C times D, where D is this right-hand side without the higher order terms. Now, this is absolutely standard, and as it is well known, has very good properties, including a very rapid convergence. However, it's also quite wild, in the sense that there is no guaranteed convergence. And practically speaking, you need to have a first guess x0 to start a procedure, must belong to some convergent domain, which is typically very small. Typically, for artificial satellites, is a few kilometers. You have essentially to know already where the satellite is. And even for asteroids, the domain of convergence is pretty small. Anyway, if the procedure converges, the limit is the stationary point. Now, what is done in practice is called, at least in this context, differential corrections, is a simplification or modification of Newton's method, in which each iteration, instead of using the matrix C nu, which is complicated because it contains the second derivative, we just use the matrix B transpose B, where B is the first derivative of the residuals, and therefore it's easy to compute by propagating together with the solution the variational equations. Maybe I should point out something. Again, I beg your pardon, this you find trivial. If you are aware that for the typical equation of motion I'm talking about, which are at the very minimum an n-body problem, there is no analytical solution. So there is no way to know the solution, the derivative of the solution, not to speak of the second derivative of the solution. So all of this must be solved by numerical integration. We can solve for the orbit, we can solve for the first derivative. In theory, we could solve also for the second derivative, but that becomes extremely complicated. And in reality, would not give a big advantage with respect to Newton's method, because the truth is that the convergence domain of Newton's method is not much bigger than the convergence domain of differential corrections. But if you use an approximation, you don't gain much in reality. You lose a little bit in the speed of convergence. At worst, you are doing an iteration more. But you don't, but on the other hand, one iteration, including the computation of the second derivative, would cost much more in terms of computational time. So what you practically do, one iteration is just C times the change in the coordinates equals D. Note that the right-hand side D is the same as Newton's method. Okay? As a result of this, even if the matrix C we are using is not a correct representation of the second derivative of the residuals, nevertheless, if this method converges to the limit point, which is a stationary point of Q. Now, the next question is, can you find all the same stationary points you would find with Newton method? The answer to this question is no. And the reason it is no is that the matrix C cannot have negative eigenvalues, because C is obtained in this way as necessary eigenvalues positive or 0. So let's suppose the stationary point is a saddle, you cannot find it. On the other hand, we don't care about saddles, because they are looking only for me. So the reason why it is reasonable to use differential correction is that yes, Newton method you could find something more, but that's not what you want anyway. Because it's subtle. Subtles, in case you ask, in practical problems, object determination of asteroids, subtle exists. Yes. I even written many years ago a paper proving that, in case you are interested, but nobody is interested really. Okay? So I think there is every justification. Apart the fact now, maybe astronomers, which have, and also aerospace engineers, they have been using this method for centuries, might find it insulting that they even question this, but there are very good reasons to use the differential correction method. There is no good reason to go back to Newton's method. Anyway, please note that the differential correction method is like Newton's method if you assume that the target function, instead of being a complicated nonlinear function, is just a quadratic function with this expression. Okay, so in a way, differential correction corresponds to a Newton method, either a simplification of Newton's method or the correct Newton method of simplified problem, in which you remove a number of terms from the target function, not only the terms of order greater than 2, but also terms containing the second derivatives. Okay, this, let me omit this because I'm going too slowly. Now I will explain the basics of probability theory which are needed. And I'm sure I will offend a lot of people because you know all this, but let me make clear that we have the same terminology. So first of all, I have to speak, okay, I'm generally speaking of continuous random variables, which are defined by probability density function, for which I use this strange notation. And the main property is that, of course, the integral is 1, and the probability of being in a given interval is given by a simple integral. Now, the most interesting kind of these continuous random variables are the Gaussian or normally distributed one, which are given by this probability density function, which contains exponential of a quadratic function of a variable. If there are only two free parameters, the mu is the first moment, that is the mean, and the sigma squared is the variance of the second moment. Now, I think that the most important question should be why to use Gaussian variable to describe the errors. Now, I have seen in many textbooks and lecture notes, especially laboratory courses, an explanation which is wrong. So let me contradict that. Many people say the reason to use the Gaussian value is because of the central limit theorem, which says more or less that if you have many sources of error which are more or less equal, and you sum the effect of these, as the number of these terms increases, the results tends to be very similar to a Gaussian. That theorem is certainly true, but has nothing to do with the problem of errors in, let's say, astronomical observation. Because there, you have very few dominant terms, and they are all different. So the hypothesis of the problem of mathematics is that there is no mathematics problem without hypotheses. So if hypotheses are not verified, the conclusion does not hold. So because the structure of the error budget of practical observation, be them astronomical, radar, or whatever, is such that the central limit theorem does not apply, period. So this is not a good reason. Then why are we using the Gaussian variables? What is the deep reason? There's another deep reason, and it's not clear whether Gauss was aware of this. For explaining this, I have to give you, I'm sorry, a couple of definitions. If I have two random variables, I can study their joint distribution, that is, the probability density in two variables. The marginal probability density are, well, obtained by integrals. Roughly speaking, the marginal probability density of x is the probability of x, whatever the value of y, without using any information on the other variable, and vice versa. Now, the two variables are independent if the joint probability distribution is just a product. Okay, now let me tell you one geometric characterization of the normal distribution. Let's suppose I have two random variables which are independent. They have equal densities, that is, the probability xx and probability y are a simple function f. And let's suppose the joint PDF is invariant by rotation. That is, in practice, it is a function of the radius or square of the radius. Okay? And they are continuous. Then these density probability densities are Gaussian, with zero mean, and the only free variable is the variance or standard deviation, which you can choose. Please note what I'm saying. I have a plane. In this plane, I give to you the level curves of the probability density, and these level curves are circles. Then I can compute what is the value of the function in these circles. And this is a very strange result, a very strong result. And the practical implication is that whenever, if you have two variables, or for that matter, of course, you can generalize these results to dimension 1000 is the same. If it is invariant by rotation, it is a Gaussian. If you think that the errors due to different observations are independent, that is, the mistake you did yesterday has no influence on the mistake you do today, and that there is no preferential direction in the space of residuals, the behavior is isotropic in such a way that the level surfaces are spheres in the space, then you must use the Gaussian. You cannot use anything else. So the hypothesis which forces the use of Gaussian is not that there are many error sources, but the situation is isotropic in the space of observation. You have no reason to prefer one observation to another, then you must use a Gaussian. This is a result which I find myself strange, but it's true. Then, on the other hand, the level curves, the level surface don't need to be spheres, they can be ellipsoid. The general multidimensional Gaussian is done in this way, where x is a vector in dimension n, and this constant is just to obtain that the integral is 1. Here you have a generic quadratic form with the restriction that the matrix C must be positive symmetric and positive definite. Okay? Then this is called a normal with mean mu and covariance matrix gamma, where gamma is the inverse of this matrix, which is called the normal matrix. Okay, let's go ahead. Now, if you have this little more complicated condition, that is, the variables are not independent, but nevertheless they are jointly distributed, they form a multidimensional Gaussian, what can we say of the marginal probability densities? Well, if I decompose my variable in two groups, then I can decompose the covariance matrix in blocks according to this decomposition of the variables. Now, the interesting thing is that gamma x is the marginal covariance matrix. Okay, that is, the marginal probability density of the variable x is normal with mean, the mean of x, and covariance matrix, the submatrix of the full matrix. And the same for y. And this is a very important property. So please remember this rule: the marginal covariance matrix is the submatrix of the full matrix. On the contrary, the marginal normal matrix cannot be computed taking submatrix of the normal matrix, but must be computed as the inverse of the covariance. Okay. Conditional Gaussians. Okay, the conditional probability density are the probability of x given information y. They are given by this Bayes-like formula. And for Gaussians, what happens is that the following rule, that the covariance, what happens is that the conditional probability of x given y is given by a complicated formula in terms of the covariance matrix. However, formula is simple if you look at the normal matrix. The normal matrix is the restriction to the corresponding subspace of the normal matrix. And then gamma x can be computed as the inverse. Okay? So there is kind of duality. For conditional, you keep the normal matrix. For marginal, you keep the covariance matrix. Okay? Now, propagation. What happens if you do a transformation to the variable from x to y? Let's suppose this is an affine transformation with A an invertible matrix. Then the variable y is also Gaussian. Its mean is the image of the mean, and the matrix gamma is transformed by a similarity, transformation, with the transformation matrix on the left and the transposed transformation matrix on the right. What is important is that this is the covariance propagation rule. This formula can be generalized even when you change the dimension. But it's actually, even if the matrix P is a rectangular matrix, then provided it has m less than n, let's say, then you can still form a covariance matrix which is smaller in dimension by this operation, even this is rectangular and this is rectangular transposed. Now, I've finished boring you with probability. Now let's get to the point. So let's suppose we have decided that the errors in the astronomical observation which are needed to compute our asteroid orbit are, first of all, the only source of randomness is the residuals. And then the residuals are a continuous random variable, each residual, with zero mean and unit variance. Of course, since observation has some dimension, you have to use some unit. It's not the same, use a radians or a degree or an arcsecond. Let's suppose they are all normal distribution, mean 0, and the standard deviation 1 arcsecond. Okay? Just the convention which has been used for a long time. And let's suppose also that they are independent. Then the overall probability density is a normal distribution with mean the vector is 0, and the covariance matrix is the identity n by n. Now we have to think of this space of m can be a large number, 100, 1000, doesn't matter. In this space, this level surface are hypersphere, and the value is just a simple function of the radius squared. Okay? Now, given this, what happens to the variable x? Well, they are also random variables. If we compute x by doing the operation on the xc, that means there is, as a matter of principle, a probability density of x given the probability density of xc. The question is how much this is. Now, to do this, you have to describe this in this way. You select the parameters. So let's suppose n is 6, and we are just selecting initial condition because it's the simplest case. Let's suppose you select the initial condition, then you compute the residuals by using for each one of them the prediction function and subtracting the observation. Fine. Then let C star be a residual corresponding to the nominal solution. Let's suppose we have found the nominal solution by using differential correction and having convergence. Then we can linearize at this nominal solution, and the derivative is the design matrix. This is the first matrix with the first derivative of the residual with respect to the parameters. However, again, you have to think that you have the space of 6 parameters and the space of 1000 observations. And we are mapping the space of few parameters in the space of many observations. The image is a small subset, is a 6-dimensional manifold in a 1,000-dimensional space. Now, since I am a mathematician, I've even given a proof that it's actually a manifold, which in case is not obvious. It has a tangent space. And the reason why it has a tangent space, that the matrix B is full rank. If it did not have full rank, the matrix C will not have full rank. But we are using C minus 1 to compute differential correction. So if it was not a manifold, differential correction would fail. Okay? Because we have conversion, we know it is a manifold. Though it is smooth, we can use the tangent space. The tangent space is described in this way. Given the change of elements with respect to the initial condition with respect to the nominal one, this gives the change in residuals. Okay? Now, to look at this tangent map is like considering this quadratic tangent function. It neglects all the other higher order terms. So what we are considering is a linear, maybe I should say linearized problem of orbit determination. The problem is not actually linear, but we use the approximation in which we are making it linear. Then we have this tangent space to the manifold of possible residuals, and we can compute a conditional probability density function on this subspace. Okay? So we know the probability of a given residual in absolute terms, just a function of the measurement process. However, some residuals are possible, some others are not. So we have to compute the probability of residuals given that they are real. Okay? Given that they have been obtained by some value, does not matter which one, of the initial condition on the other parameters. To do this, I'm sorry, I would need to make a drawing. We do a rotation in such a way that the 6-dimensional manifold is this one, and the 994 other coordinates are these. And we rotate in such a way that 6 axes correspond to the parameters we have, and 994, or m minus 6 axes correspond to the impossible residuals. Then we reduce ourselves to this condition with the rotation R. Then this vector, this second parameter, is a set of parameters, let's say 6, which parameterize the tangent space. Okay, so because the rotation does not matter, because anyway everything is rotation invariant, we can just compute the probability density on C second as conditional PDF on the subspace. By the rule we have just learned, to do this we take the normal matrix of the global distribution, and you have to pick up the 6x6 submatrix. Now this is one of these passages which is so trivial that it's difficult to explain. So what you think can be a submatrix near the diagonal of an identity matrix is still an identity matrix. And what is even more stupid, what happens if this is a normal matrix, but you have to do the inverse, but the inverse of the 6x6 identity is a 6x6 identity. So the probability density on this tangent space of possible residual is again Gaussian, and again has a covariance which is identity matrix. This geometrical, think in 3-dimensional space. You have 2-dimensional spheres. And cut these with any plane. Does not matter where you put the plane. The only possible intersection of the plane with the sphere is a circle. You cannot obtain an ellipse. Okay? Now this theorem is valid in any dimensional space. If you cut with an n plane and m-1 sphere, you get another n-1 sphere. You cannot get anything else. This is what it means. Now, this implies that in this coordinate, the linearized map has a simple structure, which is like this, because the prime component of the rotation is 0. So The matrix B is more complicated, but after rotation, it has a lot of zero and only this, which is a 6 by 6 matrix. And this 6 by 6 matrix, because this must have maximum rank, is invertible. Okay? Then, do this computation. What is the normal matrix? Normal matrix is B transpose B. But B transpose B is the same as B transpose RB, because the matrix does not matter. Then it's A transpose A. In other words, the submatrix A is a matrix square root, in some sense, of the normal matrix. Okay? Then here we are. We have this tangent space of possible residual and the space of elements or initial condition. They have the same dimension. And the map A is an invertible map, linear map between the two. So we can apply the covariance propagation rule. The only problem is that we are propagating the probability density from the space of residual to the space of elements, so we need to use the map which is A minus 1. By the covariance propagation rule, this is the formula. So the probability density of the initial condition or variables we are fitting as mean or expected value the nominal solution, and this matrix as covariance matrix. Now, a rapid computation, which is pretty trivial, tells you that this gamma is the inverse of G. In other words, the solution of the least square problem is a Gaussian PDF with mean equal to the nominal and covariance matrix gamma. But gamma, C minus 1, is the matrix which solves the normal equation. That is the one we use in each step of differential correction. Therefore, we have three things: differential correction, probabilistic interpretation, and optimization interpretation, which you define confidence ellipsoids, are one and the same thing. I like to give an even stronger statement. You can solve the problem by differential correction. You compute X star, C, gamma, and Q at convergence. After you've done this, you can decide which probability interpretation you like, because the computations are the same. Okay? The probabilistic interpretation comes for free, doesn't cost you anything. And this is a unique probability property of the probabilistic interpretation done in the context of the least square method. And then this is, when you have done this, still in the linear approximation, this is the probability density of the solution, which contains the normal matrix, which is the same we have computed to do the differential correction. Now this is Gauss 809, so I can understand about the difference in language way of thinking. Many engineers become restless if I do the mathematical proof, but I think this theorem is important enough to deserve a proof. So excuse me if you think this is annoying, I beg your pardon. Now one small generalization, and then maybe we can cut. Why the sum of squares? We have, or let's say another way, the hypothesis that the errors done in each astronomical observation are, first of all, at mean 0. There is no systematic error. Number 2, all the observations have the same accuracy. One done by the last amateur astronomer with the small scope, and the one from the less professional in the same way. And they are uncorrelated. These hypotheses are too strong. Or let's put in another way of thinking of a mathematician. You have a function Q of Xi. Why should we have, okay, it must be well convex or the minimum, but why the minimum must be in 0? And why the level surface must be spheres? After all, a generic function which has a minimum has an expression which is a constant plus a quadratic form, positive definite, but not spheres. The level, in general, the level surface around the minimum are ellipsoid, not spheres. So can we generalize to this? Can we use a target function which has this form? Now the good thing of this, that this is the most general quadratic form with which has a positive definite quadratic part. The most general quadratic form which has a well-determined non-degenerate minimum. So we would like to use this formula. And this formula, as a result, for each observation we have to remove a bias, and you have not only diagonal weights, which are different, but also correlations, which correspond to the fact that if I have done one error, a positive error next time is more likely to have a positive error as well. Okay? Because there is some source of the error which is persistent from one observation to the next, and some which are unavoidable, which I have to remove. Well, I can do that. What happens if I use this expression and I write a normal equation? Then the matrix C becomes the same thing with the W matrix in between, and the equation are the same thing with W, and of course I have to form a vector of the bias and removing this as well. And then I can, if P is the square root of W, which can be found by any of the many algorithms on the market, I can take the true residual and for normalized residual by this formula, and miracle, W and the bias disappear from the formula. In other words, if I have a more complicated model which includes biases, correlation, and variable weights, I can still eliminate them by performing a very simple affine transformation, and therefore the Gauss theorem applies in this case as well. That is, even in this case, I can compute the probability density function of the orbital elements. The only problem is that the normal matrix which appears in the Gaussian will contain W as well. It doesn't matter. And of course, if I have biases which are important, the value of the solution which I find will be different. But still, this does not make any difference. Okay? So, I think it's a good point to stop. And next time, and the next lecture, I will speak of start really speaking of impact management.
Are there any questions? Just one in the beginning, you said that Newton's method would have problems converging. What's the main reason for that? I mean, it's these perturbation elements, so, right?
No. This applies even to the two-body problem.
Okay.
So it is due to the non-linearity of the problem. In a linear problem, you will converge in just one equal n. But in non-linear problem, even in a two-body problem, if you change, suppose you have a satellite orbit, and you start in Cartesian coordinates. You start with the initial condition, which is 1/10 of Earth radii away from the right solution. Then what happens is that Newton's method brings you farther and farther away. You have a wild oscillation. It terminates with the result of completely absolute, that is the object goes to 1% in some iteration. Okay? And that's because Newton's method is extremely unstable. Actually, mathematicians like to use Newton's method to produce fractals and chaotic behavior. Newton's method has a small stability region. Outside of that, anything can happen. So if you want to use Newton's method, you have to be aware that you have already selected good orbit. And for this, you make very complicated computation of preliminary orbit. Because the preliminary orbits, as an example, the Gauss method, typically gives you a good approximation, which is good enough to be able to use Newton or differential correction as a method. But if you just make a wild guess, it does not work.
Talk to you
I have an announcement if I can, yes.